Hi, now let's move on to energy-based functions for generative modeling. So we saw in the previous sub-lecture that we can define our functions so that we model distributions, and we can do that by having a parametric function g controlled by the parameter theta and divide by the volume of that function. Now, if we define our p of theta, p theta, to be a non-parametric probability distribution like Gaussian, exponential, etc., that's okay. However, that can be quite restrictive in the sense that we might want to encode in our model definition some domain knowledge that I'm pretty sure would be very important for the modeling of my problem, and it just doesn't fit with one of my probability distributions. So what we can do in that case is that we can define an energy function and divide by its volume, and we can do that by placing our, by defining our function g to be the exponential of that energy function. So the energy function is f of f theta, or to be more precise, f minus f of theta. And then again we can simply divide by the volume of that exponential of f theta. Minus f theta is the energy function, and z theta is the so-called partition function, which is the integral of our exponential of our minus energy over the whole input space of x. Now, note here that the integral is defined over all dimensions of x, and x is high dimensional, like an image. So this integral can be quite daunting to compute. So why do we pick exponential and not, for instance, squared function? Well, there are a couple of reasons. First, the exponential couples well with maximum likelihood and natural logarithm learning. So log of p cancels each other. It becomes convenient when our p is basically exponential, right? The exponential cancels with the logarithm. So one could say that the logarithm is the natural scale for modeling the various probabilities. Our probabilities can be very large and very small, so we have a lot of differentiation, and logarithms, natural logarithms and exponentials can be the right scale. Otherwise, we'll have to choose an f theta that can be very non-smooth to model these things. Also, it's convenient because many existing distributions are based on exponential functions, for instance the Gaussian, as we saw, or the exponential distribution. And also exponential functions arise quite often in statistical physics, and we have quite good knowledge of that domain. It can serve as a very good inspiration. So what are the advantages and disadvantages of energy-based models? So of defining our neural network to return that kind of probabilities. The very good advantage is that it's very flexible in the definition, so we can basically define any type of distribution. Non-negativity and summing up to 1 is ensured like that. However, sampling can be very hard. The reason is that our partition function is not necessarily going to be tractable or easy to compute analytically. And also for sampling we have, for instance, to compute the cumulative distribution function so that we can perform the sampling that introduces another integral. Evaluating and optimizing the likelihood can also be very hard, again because we have to compute the partition function. This means that the learning is hard, and for the vanilla cases of energy models we don't really have latent variables, although that can be sort of fixed by introducing latent variables. This means that in the vanilla case we don't have representation learning. So we do assign likelihoods on our inputs, but we don't learn features, we don't learn representations. Now, what we can do or one of the things that we can do to sort of help us with the partition function is ratios of likelihoods. So the partition function is often very hard to compute. However, we note that if we take the ratio of two likelihoods, the partition functions cancel each other out. The reason is that the partition function is the same for all inputs. No matter what is the x, the partition function will be the same. Whenever we don't need to compute the partition function, we can drop it like that. So, for instance, in the ratios ratio of likelihoods, we don't really need it. It gets cancelled out. We have no partition function anymore, so that works fine. For normal learning, however, that's not that easy. We still have to compute it, otherwise we will not be able to normalize our scores. And as we discussed in the previous sub-lecture, if we don't normalize our scores, we cannot really push the model to improve its predictions, its likelihood predictions in a relative manner. Now, some applications of energy-based models, assuming a trained model, it's very nice because we can do anomaly detection. So basically see here whether the likelihood of a particular input makes sense, is high enough or not. If it's not, then it means that probably there is an outlier there. We can do denoising and restoration, so we can start flipping inputs until we obtain higher and higher likelihoods. And we can even do object classification or classification in general. So basically compare our input with a particular class label y, and then see if we have high enough likelihoods. For this, we could we would go over all possible labels and then compute or compare the ratios like that. So for different y's, y1, y2, y3, the input x remains the same. Some examples of energy models are the Ising model, which is computed as a potential over between xi and yi. Xi is the observed pixel, so let's say the noised up version of an image, and y1 is the true pixel values that we want to recover, so the latent pixel values that we want to recover. The unary term here basically gives some sort of energy on how likely it is x1 and y1 to be having the same value or different values, and the binary term here is to determine how much energy should we have when transitioning or when changing our y values between neighboring pixels that are connected by an edge. Clearly, neighboring pixels should tend to have similar values, and increasing, like having different values between neighboring pixels should be, in general the case. If not, this should mean that our unary term should account for that. Another type of energy model is products of experts. So we might want to combine, let's say, a pixel CNN with an autoregressive model and with a variational autoencoder. How can we do that? Well, with the product of experts, basically we're imitating an AND function. So if all of these experts agree, then our input gets high likelihood. If not, our likelihood drops a lot. And three other types of energy models that we're going to discuss today more are Hopfield networks, Boltzmann machines, and deep belief networks. Thank you.